Hello everyone, this is the first video for chapter 7 of the reinforcement learning course. So in this chapter, we're gonna extend the methods seen in the previous chapter, chapter 6, which were temporal difference methods, to make them slightly more general and have more powerful algorithm which can sometimes provide with better performance. So the previous chapter methods were based on single period updates, so you observed the reward for a single period and then had a single transition into the next state before making an update. Now we're going to extend this scheme to multi-period observations before updating rewards, and we're going to see why this makes sense. So the approaches presented in this chapter, they unify both Monte Carlo methods and temporal difference approaches, where both methods seen in previous chapter are can be seen as limiting case of the general approach we're going to present in this chapter. Okay, so this chapter covers chapter 7 of the Sutton and Bartow textbook. So the chapter introduces a method called the nstep TD method. Okay, so nstep temporal difference method, which, as we said, unifies both Monte Carlo methods and the TD methods seen in the previous chapter. Okay, so as we said, these two methods are extreme cases of the method which will be introduced in the current chapter. Monte Carlo are basically n step where n tends to infinity, and the TD temporal difference method seen in the previous chapter is an n step when n is equal to 1. Okay, so when you have either n is equal to 1 or infinity, you recover previous methods, but for intermediate value of n between 1 and infinity, then you get other methods. Okay, so uh, we're gonna see that the approach introduced in this chapter can benefit from advantages of both methods. Okay, so the first advantage is that contrarily to Monte Carlo methods, you can still have an update on every time step. Okay, so every time you transition into a new state and you observe a new reward, then you can update your value function. You don't need to wait for the end of the episode. Okay, an exception to this, the first n small n time steps, there won't be updates, but then after that you can make updates on every single step. Okay, so this is desirable because this speeds up computation in comparison to Monte Carlo methods. Um, Furthermore, these methods, they allow reducing the bias which was embedded in the TD method. Okay, so if you remember in chapter 6, we said that TD includes some bias because the target, the expected value of the target, is not exactly the value function because we use what we call bootstrapping. So we use an estimate of the value function instead of the true one to design the target, and this introduce some bias. Well, we're going to see that the n-step method, depending on the value of n, it dampens the impact of such bias. So we're going to see that n-step methods offer some bias variance trade-off in between Monte Carlo methods, which have no bias but very high variance, and temporal difference methods from chapter 6, which have high bias but low variance. Okay, so sometimes there's a sweet spot between bias and variance for the target to optimize the pace and accuracy of learning. Okay, so as we did for previous chapters, we're gonna first introduce the method for prediction problems where we have a fixed policy pi and we want to estimate its value function. And then subsequently, we're going to consider the control problem where we have a policy that is gradually refined through time. So one quick note here, nstep methods, they are very helpful to understand a more advanced topic in reinforcement learning, which is eligibility traces. Okay, so this eligibility traces, we've briefly mentioned them in previous chapters. They're part of chapter 12 from the textbook. However, during this course, we won't have time to cover them. Okay, but for those who are interested, I encourage you to have a look if you want to, let's say, do research or use reinforcement learning in your future career. So this topic is very useful to make reinforcement learning algorithms more powerful. If you're interested about these, then the nstep methods that we're going to introduce here are relevant as a foundational basis for these eligibility trace algorithms. Okay, so as we said, we're going to start with the prediction problem. So we start by fixing the policy pi, and then we're going to attempt to estimate its associated state value function v pi. So if you, okay, and again, we're going to consider episodic tasks here. Okay, we won't consider continuing task, but as we said, continuing task can often be somewhat approximated through episodic task because when you consider a return, the rewards in the far tail, they're very heavily discounted, so at some point you can just ignore them and approximate a continuing task with a episodic task. Okay, but for the sake of our purpose, we're going to consider episodic tasks here. So for an episodic task, the return at time t was defined as the following. So the time t return was the sum of discounted rewards until the termination of the episode. Okay, so at time t, the return is the reward at time t plus 1 plus gamma reward at time t plus 2, etc., plus the discount factor for t minus 1 periods, capital T minus small t minus 1 periods, times the reward obtained just before transitioning into the terminal state. Okay, so these are all rewards until the termination of the episode. Conversely, for TD0 methods, temporal difference methods introduced in the chapter 6, only a single reward was considered in the construction of the target. Okay, so if you recall, the target was the next reward plus gamma times the current estimate of the value function in the next state. Okay, so this was used as a target, and for notation here, we're going to use this. GT t plus 1 means that it's the return at time t, where all rewards subsequent to time t plus 1, so t plus 2, t plus 3, etc., their expected value is approximated by the current estimate of the value function started at t plus 1. Okay, so GT t plus 1 is basically the sum of discounted rewards until this time t plus 1, where we do some bootstrapping, which is we use the estimated value function to represent the approximate expected value of all subsequent rewards after time t plus 1. Okay, so the idea here is we could use something in between. So instead of considering either all rewards or a single reward, we can consider a method which the target is designed so as to consider n rewards and then use bootstrapping after these n rewards to represent the expected value, or at least approximated the expected value of all subsequent rewards after the next following next n rewards. Okay, so we can introduce the following. The nstep method entails considering this target, this as the target variable, g tt plus n, which is the sum of discounted rewards for the next n rewards. Okay, so rewards at t plus 1 plus gamma at t plus 2, etc., plus gamma n minus 1 times at rt plus n. And then for all rewards subsequent to t plus n, we can use here the gamma here, gamma to the power n, times the estimated value of the value function in the state in n periods. Okay, where here vt plus 1 and vt plus n minus 1, this is the index in the approximation of our value function. So every time at every step we're gonna increment this index here. So this is because, as we said, we have a sequence of approximate value functions, and here this is the index of the approximated value function among the sequence of all approximate functions. Okay, so one quick detail here. So this is the first n rewards, but then what happens if the episode finishes before the first n rewards? Then we set all subsequent rewards to 0 in this equation. Okay, so for example, if the episode stops at time t plus 2, and then all subsequent rewards are 0, then instead of having all these tails, so all these sum of rewards and these residual value function, then we would set all these to 0 if the episode ends at time t plus 2, for example. Okay, so if we go back to our convention where we stack episodes one at the end of the other, okay, so the rewards are basically, or the set of state action rewards are basically episode 1, then episode 2, then episode 3, episode 4, etc. So if we make a single sequence of state reward actions by stacking all the episodes together, then the more formal formulation of the target will be the following. So it's the sum of the first, next, and discounted reward, but here instead of being n, this is minimum between n and, so this is the time at which the current episode ends, minus t, which is the current time t. Okay, so this is basically the number of episodes until the termination of the number of periods remaining until the termination of the episode. Okay, because recall this notation here, this it, it denotes in which episode I we're in at time t, and t tilde I denotes the ending time for episode I. So t tilde it denotes the ending time for the current episode in which we're in. Okay, so the target is, as we said, the sum of the next n discounted rewards. If there's no termination, or if there's an early termination, it's the sum of discounted rewards until the episode. Plus here, once again, this is gamma to the power n times the expected value function. Sorry, I say expected, but estimated value function in the state st plus n. But here there's some indicator which says that this part is there only if the episode terminates in at least n step. Okay, so if the episode terminates before the next n step, so before time t plus n, then this guy becomes simply 0. Okay, so one quick note here, when do we observe the target variable? So if there's no end of the episode before time t plus n, then the target variable will be observed exactly at time t plus n. Okay, because the last reward and the last state here observed are st plus n and rt plus n, which are observed at rt plus n. Conversely, if the episode ends before time t plus n, then the episode would finish at that time here. So this is exactly at that time that we would observe the target. So the target would be observed at the end of the episode if the end of the episode occurs the before the next end steps. Okay, so this means that the time t target, so this is the target at time t or the return at time t. Not the return, the target. Okay, because return would be sum of discounted rewards, but here we do some bootstrapping, so we should say the target here, it is observed at the minimum between time t plus n, which is in n periods, or the time at which the episode ends. Okay, so again, to update our value function, we use um, similar a similar formula than we did ever before. Okay, so for of course time steps greater or equal to 0, we'll start with the second equality here. So every time a state visited at time t is different than st, then for all states not visited at time t, then the update does not change the current estimate of the value function. But when we're visiting state st at time t, the estimate for that state is the previous estimate plus the learning rate times the target minus the current estimate. Okay, so we still have the same structure. Next estimate is the current estimate plus some adjustment, which is the adjustment is always the learning rate times what we call the error, and the error is the target minus the current estimate, where the target is something whose expected value should be as close as possible to the true value function in state st. Okay, so this is the update rule. Now, when is this update done? Well, the update for state st, it's not done at time t because the target is not observed until time t plus n. Well, it could be observed if there's an n of the episode, but typically it's only observed at time t plus n. So this update here for state st, it's only done at time t plus n. Okay, so this is why the index here, it's vt plus n, because this is the value function estimate right after the reward at time t plus n is observed. Okay, one quick note here. So this is maybe a bit contradictory because I should have written here t greater or equal to 1, because for times 1, 2, 3 until n minus 1, typically the target is not observed yet. So for the first n minus 1 steps, because no target is observed, then there's no update performed in practice. Okay, so updates are only performed once targets are observed. So for the first n minus 1 time steps, there's no update. And then at time n, then you do the update for the value function at state s0. At time n plus 1, you update the value function for the state s1. At n plus 2, you update the value function at the state s2, etc. Okay, so this is how it works. Okay, so there's basically an n period lag between the time at which you do the update and the state for which you do the update. Okay, so if you're at time t plus n, you update for the state st. Okay, so we can see here using this update rule that TD0 and Monte Carlo, which we've seen respectively in chapter 6 and 5, are special cases of this approach, where Monte Carlo is the case n is equal to infinity. So basically we sum all rewards until the end of the episode. We never bootstrap to represent the expected value of the tail of the rewards in the summation by the estimated value function, whereas TD0 is the case n is equal to 1, where here in the target we use a single reward and then bootstrap exactly at time t plus 1 to approximate the expected value of subsequent rewards. So this is a more general approach which reconciles both the Monte Carlo methods from chapter 5 and the TD0 methods from chapter 6. So as we mentioned, okay, we are going to repeat a bit here. The nstep method retains some advantages of both Monte Carlo methods and TD0 methods. Okay, so as we said, the nstep method does not have to wait until the end of the episode to start updating the value function. It only has to wait for the first n steps before making the first update, or even in practice, if you're lucky and the episode ends before, you could even start before the first n steps. But in practice, if we follow the algorithm presented in the next slides, there's n time step lag before visiting a state and updating its value. Okay, so because we don't have to wait for the end of the episode, this can for making updates, this can tremendously accelerate convergence in practice. Okay, the other advantage is that we use more rewards than TD0 to make updates. Okay, so the reliance on bootstrapping for the nstep methods, where we approximate the expected value of all subsequent rewards in the target by the estimated value function, it has a much lesser impact for the nstep method than for the one-step method in general. Okay, so why is that the case? It's because if we go back here, so in the case of discounted tasks, let's go here. So here we see that for the bootstrapping term here, so this is a approximation. Okay, so if it was the true value function instead of the approximated one, then there would be no bias. But because this is only an approximation, it's not the true value function, then the target is biased in the sense that the expected value of this target is not exactly v pi st, the value function at state st. So for that reason, because this is only an approximation, this means we have some bias in the target, but the higher n is, the smaller gamma to the power n here is, so the less impact this guy has. Okay, so for very large n, this term here should be very small, whereas for small n, this term has a much higher impact. Okay, so for larger values of n, we have less. The bootstrapping term has less impact, so the bias has a smaller impact. Okay, so smaller bias is always good because it provides more accurate computations and updates. Okay, so let's go back here. So we see that when n is very small, we have high bias due to the bootstrapping term being more heavily weighted, but we have less variance because we consider a few rewards. Conversely, for very large n, we have a high variance because we consider many rewards, and each of such rewards is associated with some degree of variability. But for large n, the bootstrapping term is weighted much less heavily, so the bias is less important. And as we said in practice, what's the best value for n? Well, it depends on all problems because all problems have some sweet spot in terms of optimal bias variance trade-off. Okay, so in practice, you typically have to play around a bit with n so as to see what works best for your particular problem. Okay, so here I mentioned that this reduces bias, and this is especially true when gamma is smaller than 1. So here you might be wondering, well, what is if gamma is equal to 1? Okay, so you might think, well, if gamma is equal to 1, then the bootstrapping term has the same weight regardless of n. So it should have the same impact. But this is a slightly flawed thinking for the following reason, is because the larger n is, the more often you won't end episodes. The larger n is, the more often the episode will end before time t plus n. Okay, so for large n, in many instances, you won't get to stage t plus n in the same episode. The episode will end before, so this bootstrapping term here will simply not be there in the target. Okay, so when gamma is equal to 1, for very large n, typically that bootstrapping term will not be present because your episode will always end before you have to include this bootstrapping term. Okay, so even for gamma is equal to 1, the n step for a larger values of n will reduce bias. Okay, so as we just discussed, the n step method offers a suitable trade-off between bias and variance of the target. So as we said, Monte Carlo methods and TD0 methods are two extreme cases where in Monte Carlo methods you don't use bootstrapping, so you have zero bias, but you have very large variance because you have to sum all discounted rewards, each of which have some degree of variability. Whereas for TD methods, you have very high bias because the bootstrapping term is weighted very highly, okay, gamma to the power 1, and even if gamma is equal to 1, then it's almost always there unless you reach the terminal state exactly in the next step. But there's much less variability because you only elements of randomness in your target is the next reward and the next state. Okay, so you have much less variability. So very high bias, but much less variance. Okay. So again, you might be wondering, do these methods converge in practice? So recall, we're only considering the prediction problem here. We have a fixed policy. We don't consider policy updates here. And it can be shown so that under some technical conditions, again, here we won't do the math, so we won't discuss in detail technical conditions. You might refer to the book if you want to have some more precise indications about this. But under some technical conditions, it can be shown that our n-step TD method estimate of the value function Vt, okay, so Vt, the estimate of the value function under that method, will converge to exactly to the true value function as t tends to infinity, meaning that as more and more episodes are presented to your agent, which is learning. So to prove that, there's a very important inequality that can be used. So to prove this inequality, please do the exercises. So the exercise will show how to prove this inequality. Okay, so once you prove this inequality, then you can do a few more steps to show convergence of the estimate of the value function to the true value function. Okay, we won't do the math precisely here, but I wanted to let you know that the proof crucially relies on this inequality here, which is that the maximum across all states of the expected target minus the true value function is smaller or equal to gamma to the power n times the maximum approximating error between the current estimate of the value function and the true value function. Okay, so this inequality here, it puts a upper bound here. So this is an upper bound on the bias of the target. Okay, so this is the bias of the target, its expected value minus the true value function, and it can be shown that the highest bias across all states can be bounded by this quantity, and by bounding the bias, you can achieve through some additional steps, which we won't present here, uh, to show convergence of the value function estimate to the true value function under this nstep TD method. Okay, so now we've discussed the prediction problem in terms of the nstep method. We're now going to turn to the control problem where on top of refining our estimate of the value function, we want to continuously improve on the policy and alter the policy. Okay, so the ideas we're going to use here are pretty similar to what we've done in previous chapters. Okay, so once again, we're going to rely on the generalized policy iteration framework where we run some policy iterations to refine the value function estimate and make it closer to the true value function of the current policy estimate. And then once we do that, we can start refining our policy by making it greedy with respect to the value function estimate, which is the policy improvement step. Okay, so we're now going to present some specific cases of the n-step versions of algorithms we've presented in the previous chapter. Okay, so here uh, we can present the sarsa method for on-policy control the sarsa method we've introduced in chapter 6 is an on-policy method for control, which was our temporal difference on-policy algorithm. Okay, so the sarsa approach, which we studied in the last chapter, can be turned into an n-step sarsa. Okay, so the sarsa algorithm, which we saw in the previous chapter, is the one-step sarsa, which is typically referred to sarsa 0. Okay, but we can generalize sarsa 0 to an n-step sarsa. So recall that sarsa was, as we said, a non-policy algorithm, so we cannot have a policy estimate that is fully greedy or deterministic, because for on-policy algorithms, we need to have continuing exploration requirements. Okay, so we have to explore all the time when we generate episodes, so as to try the various actions in the various states an infinite number of times. Okay, so to do that, we're not going to improve our policy to the best or to the greedy policy, but we're going to consider instead an epsilon greedy policy to ensure continuously exploring the various actions in the various states. Okay, so again, for this sarsa algorithm, we can define the target as follows, which is pretty analogous to what we've done in the beginning of the chapter, where the only difference will be related to here, instead of having the state value function estimate v, we're going to have the action value function estimate q. Okay, because for sarsa, because we're doing control, we have to consider the action value function. This is required to make our policy improvement step. So the estimate we're going to track is the q function, not the v function. Okay, so this is why it's the q function that is found in the definition of the target. So basically, in the n-step sarsa, the target is defined once again as the sum of discounted rewards for the next n steps, where here there's the minimum between n and the number of steps before the end of the episode. So if the episode ends before step t plus n, then we put all rewards to 0 in this expression after the end of the episode. Plus, once again, this is the indicator which says this term is only present if the episode ends in at least n step, times gamma n, times here qt plus n minus 1 st plus na, where here this is the value function, estimated state value function. Well, when I say okay, this is meant to represent the value function in nstep. Okay, but here because at plus n is sampled randomly with the current policy, then the expectation of this, so if q was a perfect estimate of the value function, the action value function, then this would be an estimate of the state value function in the next step, which is the expected value of all subsequent rewards after time t plus n. Okay, so here this is our bootstrapping terms, which quantifies or at least tries to approximate the expected rewards after time t plus n. Okay, so again, the nstep sarsa update is pretty similar to the nstep td update. So at time t plus n, okay, we observe the target gtt plus n. Okay, so gtt plus n is the target associated with time step t, so state st and action at. So we can have the following rule. At time t plus n, we can update the value function for state st and action at by the following rule. The next estimate is the previous estimate plus the learning rate times the target minus the current estimate. Okay, so it's exactly identical, but the difference here is that we update q functions or action value functions instead of the state value function v. Okay, this is for the state action pair that was visited, and for all other state action pairs at time t plus n, there's simply no update that is done. Okay, so again, at each time step t plus n, we update the value of the state action pair st and at, and for all other state action pairs, we do no update. Okay, but now this is a control problem, so we must refine the policy again through time. So at time t plus n, the policy must also be made, I've written it greedy here, but it must be made epsilon greedy at time t plus n. Okay, so because we update the state value function for a single state action pair st at, then for all other states than st, the optimal or greedy policy will not change, so we won't have to update anything. But at time step t plus n, because we have updated the value function for one action in state st, we can calculate the new greedy action for state st according to the following formula. So the new greedy action for state st is simply the maximum across all actions of the q function here, qt plus n sta. Okay, so you check the action value function for state st, at least the new estimate which we've refined, check for all actions, and then pick the action which has the highest estimated value. Okay, so this is the new greedy action obtained at time t plus n, and then if you do, because we want an epsilon greedy policy, then we have we define the new policy through the policy improvement method, which is the probability of the various actions in state st. So pi t plus n simply means that this new policy is the one effective at time t plus n once we've updated the value function for state st. This is equal to the following. So this is epsilon divided by the number of state plus 1 minus epsilon times the indicator if the action is greedy. So basically this says that for the greedy action, the probability of selecting this action by through our epsilon greedy policy, it's the probability to explore and pick that greedy action, okay, plus the probability to simply select the greedy action directly associated with 1 minus epsilon. Whereas here, okay, let me think. Okay, yes. Okay, so here, if the action is greedy, this term is there. But if the action is not greedy, as we said, this term is not there, and the probability to select the various action is just epsilon over the number of states. And this here, the second equation, it says that for all other states than st, for which the value function was not updated, then you keep the same estimate of the policy because you have made no update on the value function. So of course the greedy action will not have changed. Okay, so then at time t plus n, you have a new policy, and you can use this new policy to select your action at plus n plus 1 in your episode. Okay, so at every time step, you refine your policy and you use your revised policy on every time step to continue selecting actions throughout your episode. Okay, so to generate an episode, the policy changes on each time step. Okay, so the policy varies across the episode. Okay, there also exists an n-step version of the expected sarsa algorithm. Okay, so we had sarsa in the previous chapter. We had n-step sarsa. We presented the one period case in the previous chapter. Then for both of these methods, sarsa or expected sarsa, there also exists an n-step version. Okay, so for the regular sarsa algorithm, the value, so q t plus n minus 1, st plus n, at plus n, was the bootstrapping term here. So this was quantifying the expected rewards after time t plus n. Okay, so this to have this bootstrapping term, we only consider the action at plus n, which was sampled randomly with the current estimate of the optimal policy. But recall that in expected sarsa within the target, we must not sample randomly an action within the bootstrapping term in the target. We must perform some weighting across all possible actions within the bootstrapping term. Okay, so as we're gonna see, the expected sarsa is pretty similar to the n-step sarsa. So the n-step expected sarsa is pretty similar to n-step sarsa, except that in the target definition, the bootstrapping term is slightly altered, as we're gonna see in the next slide. But for the update rule, it still remains the same. Okay, so here in n-step sarsa, the target is defined as the following. So it's the sum of the discounted rewards for the next n time steps, where we stop if the episode ends before the next n steps, plus the target, this indicator, which is 1 if and only if the episode has not ended by time t plus n, times the discount factor, times this, which approximates the expected value of all subsequent rewards after time t plus n. So this v bar t plus n minus 1 st plus n is defined as follows. So it's again the q function at state st plus n, but instead of sampling randomly an action at plus n, as for the sarsa method, we're gonna sum across all possible actions and we weight each element of the sum by the probability of selecting the various actions in the state st plus n, which are given by the current estimate of our policy. So this is again analogous to one-step sarsa, but generalizes it to n-step. Okay, so once again, similar to the one-step, we do the weighting of all actions within the bootstrapping terms, but instead of doing it in one period, we do it in n periods. Okay, so we're gonna stop here and continue next time in the next video. Have a nice day.